Hi everyone, welcome back. Today we're back with the second video of the spherical polar coordinate system. In the first video, I've discussed in the details about the r, theta, and phi, and I'll also discuss their projections about the value range of r, range of theta, and range of phi. And I've taken almost 5, 6 examples in order to make you understand like how we can assign r, theta, and phi to different shapes. So finally, we're back with the second video, and I hope you have watched the first video. If you haven't watched the video, just go and have a look on that. So let's move to the second video. Okay. See. Spherical polar coordinate system, we have three coordinates here, just like the Cartesian coordinates x, y, and z. We have here r, theta, and phi. And one more thing I discussed that we cannot define spherical polar coordinate system without Cartesian coordinate system. Okay, an spherical polar coordinate system cannot be defined without Cartesian. So basically, Cartesian coordinate system is must for understanding of the spherical polar coordinate system. That is why we can see here x, y, and z axes are here. Okay, so this is basically x axis. So this one is y axis, and this one is z axis. Okay, that's why, and they have here common origin. Now, what we discussed in the previous videos, I'll recapitulate a bit for the maybe 1 or 2 minutes, then we'll carry on in this video. So basically, this is the position vector of any point on the surface of the sphere, this r. So I told you that how much r makes angle with the z axis, that is theta. So this one is theta, and this is specific, this is theta. How much the position vector of any point on the surface makes with the z axis. Z axis is this axis, so that is theta. So basically this r has now two components. One is r cos theta. So r cos theta is along z axis, and it is another component. This r is in such a way so that it is another component lies on the xy plane, this xy plane. It's like one here is, this one is r cos of theta, and now this is here r sine of theta. I hope you got it. This r sine of theta is on xy plane. Now this r cos of theta and r sine of theta forms a plane in itself, because we know this one is now r cos of theta, and this one is r sine of theta. I can make parallel this r cos theta. So this one is r cos theta, and this one is also r sine theta. So they form a plane. And now how much angle does this plane mix with the x-axis? So now this is a plane formed by the r cos theta and r sine theta. So basically, now here we go. So this is a plane which is formed by the actually r cos theta and r sine theta. Now how much angle this plane does make with the x-axis? So that is pi. This one is phi. So again, phi is actually angle. So this is angle made by plane. Which plane? Plane formed by r cos theta and r sine theta with x-axis. If these things are clear to you, then now it's time to move on. So basically now this one is theta, and this one is phi. Now in Cartesian coordinates, you might have heard, obviously you must know this thing, that if you want to if there is some you are located at some position having coordinates x, y, and z, and now you moved in such a way in a space that you took dx in the x and dy along the y, and dz along the z. So your new coordinates here would be x plus dx, y plus dy, and z plus dz. So basically you moved an infinitesimal element, infinitesimal length along the x-axis, y-axis, and the z-axis. So your position was first x, y, and z. Now you moved a bit along a direction, and now your coordinates are x plus dx, y plus dy, and z plus dy. Similarly, in spherical polar coordinate system, if you move, then your all the three coordinates change. And if you see here, the volume of that cube here, the formed by the dx, dy, and the dz, we can make a small cube here. Okay, we can make a small cube here. One is having dx and dy, and this one is dz. So basically, its volume is volume. I'm explaining it in Cartesian coordinate system. So volume in Cartesian coordinate system, small volume. So we write dv. So that would be equal to dx, dy, dz. So similarly, what would be the volume in case of this spherical polar coordinate system? So here, if we were here having coordinates like r, theta, and phi, if we move a bit, what would be the coordinates? So finally, actually, if we are trying to find the volume, then we must have all the three lengths. But d theta, d phi are not the lengths. Are you understanding? So like here, our coordinates are r, theta, and phi. So we cannot say like dr, d theta, and d phi simply and multiple these three things, dr, d theta, and d phi. So this is the volume. No, this is not the volume, because this is the length, but this is angle, this is angle. So we cannot multiply length with the two angles and get a volume. You understand? I hope you understand the point. What students do mistake, so they simply feel like the volume element in the spherical polar coordinate system is simply dr into d theta into the d phi, which is completely wrong. Because if you understand here, so this is length, this is angle, this is angle. Length into angle can't be volume. So what we have to represent, we have to see this d theta and d phi in such a way so that it represents some length. So now there is important concept here. Okay, so this one is totally wrong. So this doesn't work. So if in the Cartesian coordinate system we have dv as the dx, dy, and dz, we must know now the dv element in case of spherical polar coordinate system. So basically, for that I'll explain a bit. I'll explain a small concept. So if you are in the Cartesian coordinate system here, like you have some coordinates here, x, y, and z, and this is x, this one is x, this one is y, and this one is z. Having coordinates here x, y, z, then you move a bit, small dl. So here the coordinates are x plus dx, y plus dy, z plus dz. Okay, now you can represent this dl vector as in Cartesian coordinate system as dxi cap plus dyj cap plus dz k cap. You know it from the high school physics. So basically this dl is represented by the increment in the x, increment in the y, and increment in the z. So similarly, what we will represent, this is called the infinitesimal vector, infinitesimal length element or length vector, length element in Cartesian coordinate system. I told you we cannot define the spherical polar coordinate system without understanding the Cartesian coordinate system. So this is the Cartesian coordinate system volume. This one is the Cartesian coordinate system. This one is the, let me put it in proper brackets or proper. Okay, so this is the volume element in case of the Cartesian coordinate system. This is the length element, small length element, or infinitesimal length element in case of the Cartesian coordinate system. Now first we'll write the length element in the spherical polar coordinate system. Okay, so let's understand this concept. So basically, if we understand this figure, this is r vector. If you move a bit here, so you move a, just give me a second. So basically, if we move in some r to r plus dr, so basically there is some vector here. This is this coordinate is now, if there is another sphere, okay, so that's having r plus dr. Okay, so this is the point, r plus dr. Now you move a bit theta, so you are here. I hope you are able to see it. Let me put it separately. This is the important concept. If you are able to understand this concept, then things would be very easy for you. Okay, now we were here having coordinate, having position vector r, and we moved to another point. So this is one of the side like dx, so this is dr. Okay, now you understood it. So this one is dr. Okay, now this is having the coordinates r plus dr. Now in case of, now you understand from here, so this was initially theta. Now if we move in such a way so that we actually move d theta, so this is d theta and this is r. How much is this? This is r d theta, r d theta. So we moved angle d theta, but along this along the sphere we moved r d theta from the if you know the formula of angle is arc divided by radius. So basically we move d theta angle in either radians or the degrees, but from the distance perspective we moved r d theta. Now this one is length, and this is also having the dimensions of the length r d theta. Okay, because this is arc. So if we write dl now, we moved simply dr because that is itself length, dr r cap because we moved along r cap, and in place of the d theta we have to, in place of the d theta we have to write r d theta. So r d theta we moved along theta cap. I told you in the last video, this is the theta cap direction, this one is the theta cap direction. Okay, now we have to write in place of something in place of the d phi. Now if you understand here, this one is r sine theta. Okay, now it's exactly like this. So this is r sine theta. Now this is phi. If we move a bit in phi direction, like this one is the d phi. Okay, how much would be this? It would be r sine theta d phi. Again arc, again angle is equal to arc divided by radius. So this is something radius r sine theta, angle is d phi, arc we don't know, we have to find it, divide by radius is r sine theta. So which implies arc is r sine theta d phi. So in place of d phi we actually move d phi, but in terms of distance we moved r sine theta d phi in phi cap direction. So basically this is the backward phi cap direction. So here this is actually like this, it's actually backwards d phi, or the phi cap. So basically we are able to make now a volume element in spherical polar coordinate system. Okay, let me write the volume element. Just focus on it a bit and try to put some pressure on your mind, and hopefully you will be able to grasp what I'm saying. So basically now this is the it isn't perfect. Now it's a bit perfect. So basically we are able to make a volume element in spherical polar coordinate system. So one is, let me call this as the dr, another is rd theta, another is, let's call this one as the rd theta, and let's call this one as the r sine theta d phi, r sine theta d phi. So finally this is the infinitesimal length element in spherical polar coordinate system. Everything will come from here. If you understand this, thing dl vector, I'm making you sure here that everything will come everything, whatever you feel in spherical polar coordinate system, or whatever you face in spherical polar coordinate system, will come from this vector, dl vector. So basically, we moved in a spherical polar coordinate system in such a way, we actually covered dr, because dr is simply length, so we moved dr. But when we moved d theta, but d theta is not length, because we have to find the volume finally. So r d theta is actually length. And similarly, this is the r sine theta. We move d phi here. So this much is r sine theta, d phi in phi cap direction. Now, tell me what is the volume now. Just like dx dy into dz gave us the volume. Similarly here, the volume would be equals r, we can simply multiply dr, r d theta, r sine theta d phi, and it has no direction because volume is a scalar quantity. So dy can be written as r dr, r square, r square, dr sine theta d theta and d phi. There is another way of what I remember. Actually, I remember it like this thing: r square sine theta dr d theta d phi. So this is the volume element in case of the spherical polar coordinate system. I hope you understand the concept of infinitesimal length element in spherical polar coordinate system, because everything will emerge from this dl. Okay, so volume, you saw that we wrote the volume from the dl. Now it's time to move on to surfaces. Actually, just like in the Cartesian coordinate system, we have the different surfaces of the cube. Now it's time to write the different surfaces. Okay, so see now. In Cartesian coordinate system, let me tell you from first the what in terms of Cartesian coordinate system. So basically, this is simply a cube, and this is simply a cube having one side is dx, another is dy, and another is dz. Now, if we look at this surface on the right, its direction is I cap, because we took this as the x-axis, and that's why this is dx. So this is x-axis. So this is I cap direction. What this is the y direction. So what is the direction of this surface? Top surface is y cap direction. What is the direction of this surface on the left one? It is minus I cap. What is the direction of this down surface? It is minus y cap. Okay, or minus j cap, whatever, right? Let's x cap. Okay, what is the direction, the one which is on the front side? So having the z cap. What is the direction of the backward surface? That is having the minus z cap. I hope you understand it. Okay, now let's erase this. Let's remove this part. Now see, I have taken here this part of the sphere. So this is the eighth part of a sphere. Okay, you cut down an orange, or you cut down an apple like that, and it would be the eighth part, because here is the center, and I took all the part on the from the top part, x, y, and z that lies above the origin. There is a portion that would be down. So it is the actually eighth part, 1/8 of the sphere. Okay, 1/8 of sphere. Now see how many surfaces it has. It has 4 surfaces. One is the curved part. I represent by this green lines. So that is the curved part outside surface of the orange. Okay, so basically, if you see it is having the direction of r. So we're just moving. So because one point, area is a vector quantity. Area is a vector quantity, and its direction is perpendicular to surface but radially outwards. Okay, radially outwards. You have to remember this thing. So radially outwards is the direction of the any closed surface, radially outwards, because we can make two perpendicular to any surface. One is inwards and other outwards, but area vector is outwards vector to any surface. So basically, if you see the curved surface, like the outside part of the orange, this part, okay, it's having the r direction because r is from origin to the surface. So if you are imagining, we have to make a vector from origin towards the surface. So basically, first surface shown by I would say green lines, or simply it's the outer surface, okay, or outer surface. So outer surface has direction of r cap. So because r we define from the origin to the surface, so it is having the r cap direction. R cap direction. Now what would be its area? Now the concept will come from this dl. This dl will tell us the area of this surface. Now it is having this direction, r cap direction. The other two will give the area, r d theta into the r sine theta d phi. Okay, the other part, the other remaining part, you have to remember this concept. This is very critical, very important. So I told you everything will emerge from this dl. So basically it has the r cap direction. Now what would be the area? dA will be what would be the dA? The remaining parts, because this part will give the direction, this remaining part will give the area. So r d theta into r sine theta d phi, r sine theta d phi. Okay, r cap, because its direction is r cap. Okay, so we can write it r square sine theta d phi r cap. So this is the dA. Okay, this is the first surface. Second surface, let's move to the second surface. Let's take this one. Okay, this purple one we take here, this purple one. So its direction is phi cap, because we define phi cap direction as like this going backward, because this is the phi in which the this is the direction in which the phi is increasing. This direction I told you, the increasing coordinate direction will give the direction of phi and theta and r. Okay, in which direction the coordinate is increasing. So basically this is the phi, we're moving in that direction in order to get a phi plus d phi. So this surface is backwards, like its direction is phi cap. If you understand its direction is phi cap, then so phi cap is the direction. Let's say this is the surface 2. Let's say another surface 2. So this one was the surface 1. Now surface 2, I would say a bit purple side. Now its direction is phi cap. Now what would be its area? The area would be decided by the other two sides or other two elements. So this part will give as the direction, the other two parts will give as the area, r d theta dr, or r dr d theta phi cap. Again, let me check, r dr d theta phi cap. Okay, now let's move to the surface third. Okay, so let me, which one will let's take this blue side. Okay, the blue side. So if you check here, so if we move in this direction, see, if we move in this direction, we get phi cap. If we move in this direction, we will get minus phi cap. I hope you got it. So surface third will be actually, if you check from here, it is having in spherical polar coordinate system, it is having minus, because it's going actually this way. Okay, so it's having minus phi cap direction. So it's having minus phi cap direction. What would be the area? dA, the other two sides, just like this, r dr d theta minus phi cap. Okay, fourth. Now the remaining this side, so it is having the downwards direction, and I told you this is the theta direction. Theta is increasing in that way. This is theta is going like this way, like this direction. So it has, it is going a bit like this. So it is having the theta cap direction. So if it is having surface 4, so it's having theta cap direction. Now what would be the area of that thing? That will be decided by the remaining two parts. So this will decide the direction of area. Now these two will decide the magnitude of the area. So r sine theta dr d phi, r sine theta d phi and dr, r sine theta d phi dr, and theta cap, so dA would be equal to the r dr sine theta d phi theta cap. So basically, what we learned in this video, how to write the dl element in spherical polar coordinate system, how to write the volume element in spherical polar coordinate system, how to write the area of any side in the spherical polar coordinate system. So you have to check just what is the direction of that area. And how you check the direction of area? The vector perpendicular to the surface radially outwards. Okay, this is a very important, radially outwards perpendicular to the surface. If you check the curved surface, so this is the outwards r, so the other two will decide the magnitude, r cap will give the direction. If we check this one, it has the phi cap, so phi cap will decide the direction, other two sides will decide the magnitude of that surface. Now if we look at this surface, so it's the theta cap, the other two, this theta cap will decide the direction, other two will decide the magnitude. And if we look at this side, it is having the minus phi cap direction. This will decide the direction. Other two, other two things, or the other two parts of the dl vector will decide the magnitude. I hope you got it. In the next video, I'll try to write the unit vectors r cap, theta cap, and phi cap, because that is very important when we try to transform a vector from one coordinate system to another coordinate system. Unless and until you don't understand what are the unit vectors in case of spherical polar coordinate system, you won't be able to transform any vector from one system to the another system. And there I'll tell you a transformation matrix actually, and I'll give you the proofs of how we get the rotational matrix actually. I hope you understand the video. Thank you so much.